Well, good afternoon to those on the East Coast and Central Time Zone. Good morning to those Mountain Time Zone Pacific. This is watching the Laboratories Academy IoT Compliance Series webinar today on the mobile power and the Internet of Things with our guest presenter, Lee Stogner. Before we get started, I want to give a few housekeeping items. When you're using your WebEx to view the webinar, you can, for the best sound, we're making sure everybody's microphone is muted. We're also recording this event, so you can rewatch it later, and for those not able to make it at this time, can watch it at their leisure. And then we've also got some controls on there. You can do a full screen view by going to the view icon, drop-down menu in the upper left corner of the WebEx window, and selecting full screen. You can go back to normal view by hitting escape key. There's also chat and Q&A comments. This is how we'll be collecting questions for the end of the presentation because it's hard to get with everybody's audio line to get questions through. So if you've got questions that come up here and there, just put them there and they'll be queued up, and I'll be preparing those for Lee at the end of the webinar. Also, any we don't get answered today, we're going to give you the opportunity to get those answered through our LinkedIn group that Lee Stogner manages. I'd like to introduce our speaker for today, Lee Stogner. Has served in executive positions in several companies that drive improved business performance using technology and project management. With over 35 years of experience, and including a wide range of industries with companies such as Digital Equipment, Floor Corporation, and Rockwell International. He's also very involved in professional activities, including the IEEE. He has served as the chair of the Carolinas Engineering Cluster, and he was a past director of the IEEE Board of Directors. He's currently promoting the development of the Internet of Things through his participation in the IEEE Smart Grid Initiative, the IEEE Transportation Electrification Committee, and is a member of the IEEE Internet of Things Initiative. So with that, I'd like to turn this over to Lee, and he'll be taking you through his presentation.
Well, thank you, Mark. This is Lee. Mark, can you hear me?
Yes, you're coming through loud and clear.
Okay, just checking. Well, we are going to talk about the full range of how we're putting energy into a small box or adapting to energy that's in the environment at locations that the Internet of Things wants to drop into and displace a sensor, a network, or otherwise connect to the world. So as Mark said, please try to save your questions until the end. And we're going to do some things after this presentation to give you full value from what we're about to talk about. So I'm going to go through the slides somewhat fast. I want you to take note of the terms, the concepts, and see what ideas it might trigger in your mind. A copy of the presentation will be available for download after today, so you don't have to worry about taking lots and lots of notes. And on the IEEE Battery LinkedIn group, we're going to open up a special discussion area just for this presentation. So if you think of something after the time limits of today, or just simply, gosh, I wish I'd asked this yesterday, we will have a place that we will monitor for some time to make sure that, after the fact questions are fully covered. I'll try as best I can. And for the other experts that are on this webinar, you're welcome to ask questions and contribute as well. So with that, let's get going. For an agenda, we're going to cover devices, mobile power, solar-powered IoT, energy harvesting, energy production and storage, and where it's all going to go as we conclude. Initially, I want to showcase this. This is the range of things that the Internet of Things has done in small things that are audio or consumer-based, graphics that are on your arm or otherwise very small, sensing devices, thermostats, sensors on your arms, sensors in your running shoe, connectivity where things are being either plugged into, sensed, or otherwise networked back from something small back to the world, and the network. The network of old has been completely replaced. Some of it's wireless, some of it's wired, but the protocols are very smart and very fast. So keep all that in mind as you look to fill applications that you want to work on. This is a slide that shows what the world is up to right now. Many of these companies that you see on this screen didn't exist 5 years ago, much less, in many cases, 2 years ago. So the world of IoT, especially the mobile world, is extremely entrepreneurial. So if you've got ideas, you could be on this chart next year. And I think it's a great place to be in terms of the possibilities for business, commerce, and a lot of reward for the people that put the hard work into it. The IoT device landscape, something has happened just the past few years. All the billions of people that live on this planet have now been outnumbered. Back about 2005 or early 6, we achieved a milestone that there's more devices out there that are connected than there are people. So with so many devices per person on this planet, are we collecting the right information? Are we collecting too much information? I did a little inventory in my home a week or so back, and I've got over 100 things in my house that have an IP address, from my Fitbit to my printers, my computers, my wireless routers, my Amazon Echo Dots, my wireless cameras, all kinds of things that are in play, collecting information, and I hope only sharing what I want to have shared. Wireless IoT sensors. This seems to be part of the big growth of mobile IoT. According to market researchers, IHS, shipments of home devices will grow to 200 million by right now. And when I talk to developers, I say, wow, that's a great idea for an IoT device. How are you going to power it? And some of them, I should actually say too many of them, look at me and say, I don't know. I hadn't thought about that. So wireless devices, small remote devices, all kinds of devices will require power. And that's why I think the topic on this webinar is so important to people that want to make sure that their device will be powered on day one and powered on day in when the device is still being used. A question that comes up is, will your device still be powered well beyond its application? And how many billions of devices will be scattered around the world, still talking, but the servers in the sky aren't listening anymore? So something to consider. Powering IoT devices. They could be anywhere, being accessed anytime. So a lot of these devices are doing critical monitoring and control tasks. And for all these things to work, we've got to make sure the functionality requires and justifies the great expense in many cases just to get power to that device. So we've got some prerequisites that want to make sure you get the right power at the right time and quantity to all these devices. So as we progress through these slides, we'll see some of the things that are happening right now to provide power, and some of the things that are in the works that could provide power in the months and years ahead. So a key challenge for IoT is how to deploy wireless sensors. The challenges include, is it worth running a power line to the device? What about the battery operated ones? Does it justify the cost to go find the device, do a quick check to make sure that the battery is at a point that needs to be replaced, and then replace it, because there's cost and time involved with all this monitoring and maintenance. So imagine a scenario with billions of sensors. What is the battery cost, which may exceed the cost of the device itself, and this enormous scale of maintenance. So right now, we've got some power sources for IoT that include non-rechargeable batteries, such as alkaline, very dependable, very cost-effective source of power, but it has a finite life that may far exceed the convenience and the requirements of the device. Rechargeable batteries, hey, that's going to get me months and even years into the future with power. But even rechargeable batteries, even the best batteries, have a finite number of recharge times before the battery simply won't retain the charge. Printable batteries, solid-state batteries that are in the pipeline, supercapacitors made out of graphene and other types of materials, and energy harvesting. I'll let you know what that means shortly. So, one handy tool for calculating how much power you might need for operation and certainly the life of the IoT device is the Farnell Element 14 IoT Power Calculator. Here's a web address. You'll get it on the download version shortly, but there are tools out there to let you discover what that device is going to consume times the time it will be in operation. A generic energy model for IoT devices. On the left-hand side of the screen, there's the idea of energy harvesting. That could be a battery, it could be solar cells, it could be a small local wind generator. Well, you've got to create or capture the energy. You've got to put it into a buffer for the energy, which is can translate into a battery or some other device that will store the energy. And then we go into the application, and the system, its sensing ability, and the radio that sends this important data back to the home office. And all of these individual pieces each consume power, and you have to plan for these pieces of the application or pieces of the device to understand the total impact of getting energy to this remote IoT device. So, factors that can affect the battery life of an IoT device. The processor sleep mode. It may look turned off, but the clock is still going, waiting for you to actuate it or the information to show up on the sensor or for you to push that button. Peripheral power consumption. You know, what's the application doing when it's running or it's sleeping? And then the IoT communication technologies. Is it using standard Wi-Fi? Is it using something called Zigbee? Is it using Lightwave? Just how is it communicating its data up a level or to the next sensor? Here's the concept of energy harvesting. If you were to sit at your desk or at your home easy chair, you're being impacted by energy that is simply in the air. And I mean radio frequency energy. Radio stations, cell phones, satellite, there's a variety of RF energy that's all around us. And up until now, it's been sort of a test question from a theoretical standpoint of how could I use all this energy that's always turned on? Well, electronics is getting ever more efficient. The ability to design small effective antenna arrays to capture that energy gets better all the time. So we're at that point where some electronics devices have demonstrated the ability to provide a function solely on the energy that it just grabbed for free out of the air around us. So don't discount this idea of grabbing and using energy just yet. Energy harvesting is attractive, but deployment can be challenged. I mean, the RF signal out of the middle of the forest may not be as strong as at your desk, and temporary storage of this type of power may exceed the ability to power the device, because you're still consuming energy as it passes through and then out of that energy buffer. Don't plan on using your consumer device on your wrist anytime soon for energy harvesting, but hey, in another generation of electronics, you never know. And lastly, the networks that connect all of us together is looking ahead to the world of energy harvesting. There's a networking protocol called Zigbee. And in version 3 of Zigbee, a lot of folks are working together to make the standard energy harvesting ready. So if you're working on one of these teams, good luck. We're going to need you in the future as we deploy another 10 billion IoT devices around the world. Zigbee 3.0, it is a foundation for an interoperable protocol for the industrial Internet of Things, otherwise known as IoT. Other applications will also use Zigbee 3.0, especially home automation, or anywhere you need something reliable for moving information in a fashion that is dependable, as well as being able to handle the volumes required for all these devices all over, and maybe even in your own house. Okay, what about solar? Solar is already being used in very remote applications, such as far away on a mountaintop or out floating in the sea. Solar panels are providing enough energy right now for capturing, storing, and transferring the data to the host. And in the days ahead, solar panels are getting ever more efficient and able to transmit more and more energy. So the abilities to transmit data further via a wireless link or transmit more data is happening right now. So put solar power on your short list for powering remote IoT devices. There are kits out there in the marketplace. You don't have to wonder, what do I have to go collect to try out my ideas? These kits are available. They have electronics for capturing and storing both data and energy, and then doing a local bit of signal conditioning on the data to make sure it is compact and error checked before it flies through the sky to the host up above. Now, the network itself needs to be made ever more efficient, because the energy that we save at the point of data collection, at the point of data transfer in this network, and also at the point of data utilization, all this adds up across the big network to give you a full indication of how much energy for one sensor is required, or how much energy for a billion sensors is required. And there are applications out there that will require a billion sensors to effectively manage the domain that these applications are being developed for. The LPWAN features, they can be long range. They certainly need to have a maximum life. Multi-usage. It's more than one sensor and more than one customer. And yes, we do need to manage the costs and reduce the infrastructure required to put all this together and keep it running for a time period that could be years and years. how are we producing energy today? This is going to be your checklist for what your application will need to work. Today, we still have a lot of fossil fuels being burned to create energy. We have hydro, we have wind, we have solar, we have nuclear, we have geothermal. In fact, geothermal keeps the country of Iceland going, and then other mechanical wave action on the coast, gravity powered devices. I'll show you a picture of one, and others that are quite innovative, and it helps our fellow mechanical engineers be productive. Energy, the big picture. This is a slide I'll show in just passing. This slide is updated and maintained by US DOE, and it's amazing, if you look at the slide, how much energy is being produced, transferred to a variety of applications, and also how much is rejected. So this is the big picture. So the goal of the people on this particular webinar is to use as little of this as possible, or perhaps invent some new ways of creating energy for the future. The energy cycle, moving from left to right, we either buy it, we make it, or we transfer it from some source. Certainly part of the goal is what we don't use, sell back to the grid, because your neighbor down the road could probably use what you're not using. So you have to measure what you're using. You have to perhaps add to what you're buying to maximize the energy available for your application. And you need to convert it to the kind of energy you need for your application. So AC/DC inverters and protection devices are certainly required. One of my friends is a fireman, and one of his biggest hangups when going to a fire at a modern day building is, what about the solar power? Is it turned off? Even though the power may be turned off in the big office building, the solar grid may be operating just fine, putting potentially hundreds, if not thousands of amps on a wire that some firemen may touch. So we need a better balance for the future. We want to reduce pollution. We want to manage the carbon emissions as best and as much as we can. And we want to put more renewable energy onto the grid. If you look at the news, about every day there's a new milestone being reached. So, this and that country just lived off the sun and the wind for X number of days that they could never ever do before. And I'll give you in a few more slides how the island state of Hawaii is quickly reaching that point of self-ability to produce their own energy. Energy efficiency. We've got to be smarter about the so-called smart grid. We want to make sure that we still have energy when disasters happen. Think of Puerto Rico. Move more of our energy into the world of transportation to reduce our dependence on fossil fuels, and make sure people in general have access to electric energy. Building a new energy goal. All this renewable energy, that's a good thing. But the sun doesn't shine all the time, and the wind doesn't blow. So you see a picture of my hero, Elon Musk. He has battery and control systems that will help balance out the grid between day and night, and wind and no wind. And he's got some very impressive achievements that shows that this will work. Energy storage technologies. There's a lot of ways you can store energy, not just in a lithium or lead acid battery. There's other things such as molten salt and other things that we'll talk about shortly. Energy can be stored, and there's a lot of imagination going into just how you can do it, because you might or you will need it for a remote group of, say, 1,000 IoT sensors. Think about it. So, specifically, energy storage for mobile devices. Here we go. This is the periodic table as it applies to batteries. And when I say batteries, I'm talking about a cathode, an anode, and some sort of chemistry in between for centuries now, because I'll show you a picture of a battery that dates back 2,000 years in a moment. The electrochemists and battery scientists of that day have looked at this chart as the finite limit of the things that can be blended, mixed, or otherwise put together to store electric energy in a chemistry-based battery. Well, as we go further, you'll start to note that some of the ways we're storing energy now, or is on the drawing board, doesn't appear on this chart. That was the rule of battery law, if you will, up until about 5 years ago. Smart people can push their horizon in many ways around the world. Okay, here's a battery. They're called the Baghdad battery. Terracotta jars, copper cylinders separated from an iron rod by a non-conductive stopper, and filled with an electrolyte, of which they had a few even 2,000 years ago. And why would you need a battery 2,000 years ago? Well, people had discovered the benefits of electroplating, and this is where they got the energy for doing that. If you fast forward 1,000 or so years, all of a sudden we had a renaissance in the early 1800s of how you can store energy in a chemical kind of battery. You have the voltaic pile, invented by Alessandro Volta in 1800. Zinc and copper, brine, and you can store energy. The Daniell cell in 1836 by John Daniell. The lead acid cell by Gaston Plante in 1859. And if you want to talk about a device that has had a lot of use and popularity, it's the lead acid cell. Go raise the hood of virtually any vehicle on the planet, and you will see a lead acid cell that was cheap produced, reliable. It works in freezing weather, hot weather. You can shake it going up and down a mountain road. Extremely reliable, and at the end of life, you can recycle it. So don't count out the lead acid cell just yet. It has an energy density that fits almost every application of today, and it comes in a lot of packages that exceed what you see under the automobile hood, and it goes from small to big, extremely scalable. The next one is the zinc carbon cell, 1887 by Carl Gassner. The nickel cadmium battery, 1889 by Waldemar Junger. You thought that was a recent thing for your old Sony Walkman, but no. These chemistries have been around since, in this case, 1899. The common alkaline battery, 1955, Louis Urey. And then the nickel metal hybrid battery, 1989. Well, about that time, the abilities and the smarts required to develop the next generation battery exceeded what one scientist could do, because you not only needed the chemistry, you needed the packaging and other things required to manufacture and put on the shelf for someone like me to put my ancient Walkman on the grid, or power up my brand new wearable device. That takes us to now, which is lithium and lithium ion. Have we achieved the perfect battery? Well, it's fairly cheap to make and to sell, but there's some gotchas with this chemistry. It starts degrading the very moment it comes off the manufacturing line. It's very susceptible to problems that can make it heat up. The Dreamliner is a good example of that. A lot of laptop batteries have heated up and caused problems. So lithium, like a lot of engineering applications, are good within bounds of that application. So what can we do? We'll talk a bit more about that in just a moment. An overview of other kinds of batteries, real quick. The mercury battery, cheap to make, small size, could last 5 to 10 years in all kinds of applications, but the problem is it contains mercury. And when it gets out of the mercury encasing box that it can poison people, especially little kids who find a mercury battery on the floor. The silver oxide battery, it costs but has great energy density. Atomic batteries that create heat that's picked up and translated into energy with thermionic converters. A good example of this is a chunk of plutonium that's on the Voyager satellite that has now achieved going outside the solar system. The heat from that piece of plutonium is still powering that spaceship. Beta voltaics, using atomic decay to create movement of ions and then electrons. Terminology. We want to make sure we all speak the same language. Primary batteries are batteries that are disposable, alkaline. Secondary batteries are batteries that we consider to be rechargeable. EMF, electromotive force, or voltage. Ampere hour. Coulombs is one way of measuring. Is how much of a charge you've got. A watt. Joules is the base measurement. It's a measure of energy. And then AH, which is a measure of the watt hours divided by the EMF. Okay, quickly, we'll run through these slides to get more to the application. Alkaline batteries, pretty good energy density, very steady voltage, reasonable energy, but they burn out, if you will. Secondary batteries, nickel metal hydride, nickel cadmium, you've got the memory effect in nickel cadmium. These are good for consumer applications, but you can't depend on them to power an application out in the quote field for months and certainly not years. Lithium ion and lithium ion polymer. Great energy to weight ratio, no memory effect like the other kind of battery. It does discharge while it sits on the shelf, and like I said, it would degrade from the moment it's made. It requires protection circuits to protect the battery and make sure it doesn't do something like get hot. And the lithium ion polymer batteries retain the ability to have a high energy, but it also is flexible. If your smartphone has a little bend to it, if your headset bends between the speaker and the mic, this battery can bend around the curve. Kind of interesting. Lithium-ion batteries. This is a picture of the battery that was in the Boeing 787 back in 2013 that had a flaw. You can argue that it was design. You can also argue that it was how it was manufactured or used. But the bottom line, there were things that went wrong in this particular battery design. And the typical particulate or contaminant that makes lithium heat up is water. Water in the atmosphere of a manufacturing plant that's making lithium-ion batteries can make dangerous batteries that you certainly don't want to take into a critical application. So what is the solution? Much cleaner, much drier manufacturing, and ways to monitor the batteries in a more comprehensive way to make sure that the heating doesn't create smoke, doesn't create fire. So still, what is our most annoying problem in all this? Your batteries don't last. And we're going to be using more and more of these things virtually any minute. And I've got a slide right here that shows that the demand for portable electronics and the internal or readily available power sources is just going through the roof. And this is our challenge, to follow this curve from left to right as it just goes straight up by or before 2025. So, how do I improve the battery life of mobile devices? Well, you can make the electronics more efficient. You can make the software more efficient. You can be more efficient at charging the battery, whether you're remote with an attached solar panel or you're a bank of batteries in a factory or some process where you do have access to charging, but you still need to be careful about the amount of energy required. And then lastly, improving the technology and the overall energy density of the battery itself. So in the world of mobile power, the device that's driving that business is the term wearables. They're used in military applications, industrial, infotainment, fitness and wellness, healthcare and medical, and they're everywhere. You've probably got a couple of them in your pocket or in the pocket of your jacket right now, and you'll have more tomorrow. A couple of quick pictures to give you a full benefit of how power needs to be mobile. Here are TVs and cameras and fun devices all require mobile power. Here's some more that get into the medical side of portable devices. So, quickly, we'll throw a few things at you that go beyond lithium and lithium ion, because while it's a good battery technology, if you manage it, it's also finite. There's only so much of it in the world, and there'll be battery applications in a century that everyone will depend on, and we want to make sure that we have enough of these materials to last a long, long time. So, here is a mobile battery technology based on sand. And for the moment, we have a whole lot of sand available in the world. It's good for making silicon, and we think it may be good for making batteries. Here's researchers that are getting closer to making sure that the lithium battery, as it's being made, is still the lithium-ion battery that's deployed and used 6 months or perhaps even years later. There's different ways to make improvements in lithium-ion technology. The chemistry is one, and also the cathode and anode is another. So this research scientist is working on improving the connections into the battery to make sure that the maximum energy is captured and then transferred to the application. And again, you'll have a hard copy of all this as you download it, this presentation. A Japanese battery manufacturer has come up with a way of making a dual carbon battery, as they call it, from cotton fibers. A battery technology that you can grow. Talk about being replenishable and renewable. Neat trick. Another way to store energy is in sugar. And with the variety of ways in which we can create sugar in the world, this has a lot of potential. New mobile battery technology, a mix of really thin zinc and polymer batteries, can make batteries that go beyond lithium, quite flexible, which is good for the application, and quite scalable from small to bigger. Energy can be stored in a capacitor. So here we have miniature graphene-based supercapacitors, as they're called, that can store energy between the point you created or the point where you consume it. Another way in which materials can store energy is there's a company where I live making batteries, as in supercapacitors, from sheets and sheets of aluminum foil that's rolled in a proper way, such that if you capture energy in the strokes of a heavy earth-moving machine, you cannot waste half the energy, as the stroke and the recovery takes place every time that piece of equipment does its job. Here's an example of batteries getting higher and higher energy densities, and it's again they're improving the negative electrodes, so it can store more or affect the storage of more as energy passes through it. Okay, this is a serious picture. Remember when your mother said, "Don't shuffle when you walk"? Well, that shuffling creates static energy that can be readily converted into the flow of electrons to power a wearable or very small electronic device. So, serious point of technology. It does work. We just need to focus on creating more static electricity from the ways that it can be produced and using less of it in the electronics. We mentioned sugar before as a means of storing energy. Glucose, that we all have our share of, is also a way to potentially power medical devices. So stay tuned for this. If this is as effective as the scientists say it will be, you may not have to go through those operations required to replace batteries as often for your pacemaker. And if you think about the world of Hollywood, didn't they make a movie where human bodies produce energy to power the evil robot overlords? Something to think about. Okay, quickly, the fuel cell. This is actually an old technology. It was made very practical back in the early 60s because we needed energy that could go to the moon. Here's a picture I took. It's in the Los Angeles Science Museum. This is a fuel cell that went to the moon. If you look at the wires associated with this fuel cell, they're as big as your finger, which means it was creating a lot of current. Go see it. It's still there at the Science Museum. For fuel cells, one of the challenges is coming up with the universal package to make the fuel cell into a battery kind of devices. So on the picture in front of you, here are some devices that are already being powered by commercially available fuel cells. And if you're a sci-fi buff, the Terminator, the evil robot, was powered by fuel cells. You can try that question on your kids tonight. Here's a practical application of fuel cells. The biggest limitation these days with smartphones is on day one, you might get a full day based on our charge, but the challenge is, can we get 2 days, 4 days, 6 days, maybe longer? What you see between the tweezers in this example is a working fuel cell that can power an iPhone 6 in this application for longer than a week. So don't rule out fuel cells yet. A well-designed fuel cell could power your remote application for weeks, maybe even a month or two, which might serve and meet the specifications of your application. Here's Mr. Dyson. You might remember Mr. Dyson of vacuum cleaner fame. His very efficient vacuum cleaners have made him a billionaire. So what do you do for your next act if you're Mr. Charles Dyson? He's focused on solid-state batteries, a different way of producing the chemistry that will power the future of remote and mobile IoT. There's also a rumor that he's going to make electric vehicles. Wow, he could power vacuum cleaners and electric vehicles with the same technology. Pretty smart guy. There's technology available now where the electronics are ready and able to store energy in a supercapacitor. So all of this is starting to become very common. A piece off that shelf, a piece off from another shelf, and you've got a smart energy system that's portrayed in this picture of energy production, storage, monitoring, and then use. Neat trick. It also will apply to things that will be all around your home. One scientist says he's going to replace the dangerous mercury cell batteries with a new type of coin cell battery that could run for 10 years. He might become the next billionaire. Electronics firms such as Samsung and others, they're working very hard to overcome range anxiety in electric vehicles, which are very mobile. Samsung says with their technology, your car battery can be charged in 20 minutes. That's just long enough for you to hook up at the electric charging station, go buy a drink, maybe have a cup of coffee, come back, and you're ready to go further on your trip. Here's another example of battery technology based on sodium, very common in the world. Here's a device for capturing waste heat. If you remember that big energy slide I showed you, it looked like about a third of all energy produced was going up the proverbial stack. Well, a lot of energy goes up the stack, out the tailpipe, and it's just simply wasted. So these little thermodynamic devices that you see right here can convert a lot of the waste energy into usable electricity. The gravity light. We mentioned gravity was a source of energy. Well, like the old cuckoo clock, if you can hook a generator up to a chain and a set of lights, you can provide light at night to a lot of people. Just imagine if you're a remote village and you've got a child who wants to read at night, a gravity light can give them an entirely new future beyond where they're living right then. Quantum dots made from fool's gold, another source of battery technology. There's a gentleman by the name of Lonnie Johnson who became very rich with a device called the Super Soaker. And if you've got kids that go to the beach or to the pool, you know what a Super Soaker is. Well, he is taking his wealth and coming up with new ways of making solid-state batteries. So all of a sudden, the world is full of people who is very able, from a smart standpoint and a funding standpoint, to create the next perfect battery. Here's a clean battery made from a combination of things we've talked about already. Here's a battery that takes solar energy that's used to redo the chemistry of a battery and give you more energy for tomorrow. Now, back to the Dreamliner. If the Dreamliner battery had in its design a special layer or separator that this talks about, when that separator is damaged or punctured, the separator operates like a big fuse and shuts that battery down. It can prevent all types of battery failure just by this basic mechanism. And there's a firm called Soteria who is going to license this technology to a variety of manufacturers. So it'll be available from a number of companies and in a number of applications reasonably soon to help stop and greatly reduce the lithium-ion-based fires and problems of the future. Very nice trick. Keep an eye on this company, Soteria. Mark, how are we doing on time?
Doing well. Got 10 minutes left till the top of the hour, but however you want to finish the rest of it.
Okay, here we go. I'll make sure I do about the top of the hour. So, electric vehicles. Here's my dream car, a next future generation BMW Roadster. It requires batteries as well. And batteries are being used all through transportation, not only cars, but trucks, trains, ships, airplanes, utility vehicles, and so on. Where you need movement for transportation, companies are looking at doing it with electricity. And the source of the energy can be the rail below the train, a wire above the train, fuel cells, lithium batteries, wireless energy transfer, and next generation batteries based on the technologies we've looked at in the past few minutes. And the overall benefits, a whole less pollution. You can take out things in the vehicle such as transmissions, all the pollution controls in the average gas-fueled cars. It's going to make vehicles simpler to build, cheaper as soon as the price of the batteries go down, and a whole lot cheaper to maintain over the life of the vehicle. Are there issues? Range anxiety. That is being fixed with new vehicles that have a range of 300, 350, and even 400 miles between charges. How will we make all the batteries? Well, here's Elon Musk's Gigafactory. It's up and in startup mode right now, and the rumor has it that the earth movers are clearing a space right next to this factory just as big for, we hope, yet another Gigafactory. And Elon's not by himself. There are other companies and countries around the world building their own Gigafactories. Where are we going to get the lithium of the future? Some scientists are saying that lithium can be extracted from the remains of super volcanoes. I'll have to trust them on this one. So we're not completely out of lithium just yet, but for the moment, it is quite limited on the planet. Electric vehicles, very quickly. They're here, they're now, and they're growing in popularity as the price of gas goes up. And if you check the price on the gas you bought last week versus 2 months ago, you know what I'm talking about. Thomas Edison, very quickly, he invented and sold an electric vehicle basically over a century ago. It had a range of 90 miles. He used a nickel iron battery structure. Well, the Nissan Leaf, the first generation, had a 90-mile range. Now, it didn't have the flexibility of free air conditioning like the Thomas Edison vehicle did, but electric vehicles is a workable technology that has been coming for quite a while. There's a Holy Grail project. Lots of companies are competing for a prize to create the ever more perfect electric vehicle. For the grid, very quickly, we've got to balance out the grid and make all that energy in the daytime work all the time. So companies such as Siemens and GE are finding ways to store energy in thermal systems like you see here. Chemical systems based on hydronium ions. I don't think I covered that back in college. Something called the redox flow lithium battery, where a principle where the chemicals in these two tanks, as they flow next to each other in a pipe, makes electrons move. That sounds like a generator. What's neat about this is this particular concept has potential to scale to what a utility will need to produce to power tens of thousands of homes. So stand by. So a couple of examples. I mentioned Hawaii. Elon Musk has come to the rescue, and he's providing battery systems that will help them make their electricity last all night long. Google says they have reached the milestone of not having to use any fossil fuels at all. And here's an example of them taking their solar and wind energy and storing it in vats of molten salt. Here's my buddy, Elon Musk. With the Prime Minister of Australia, they had lots of problems. He said, I will fix them in 100 days. Well, he met the schedule. He brought in his energy storage and management systems, and now the energy that Australia produces for renewables is being used and maximized through the art of energy storage and management. Thank you, Elon. So how do we make all this stuff energy compatible and pluggable? Well, notice the icon in the lower right-hand corner, IEEE. We have a variety of standards that allow us to capture energy, transfer energy, convert energy, and power things correctly and efficiently from parts made all over the world. And like the standard says, if we have a little too much that we're producing from our own solar and wind generators, we can put the power back on the grid. So what are our challenges? Make sure we're spending money on the right technologies and we're deploying in the right way. I apologize for picking up the pace. There are ways to make sure we maximize the potential of the energy. Here's Qualcomm and their quick charge technology, which is going to make your smartphone go a bit faster and further. Software. We've always seen that argument at the restaurant between the Android people and the Apple iOS people. Well, Android lost. Their software was less efficient than Apple. So Android now is making great strides to make sure that whatever the device is, and it's sitting there either in operation or in sleep mode, is using less energy than before. My favorite electric vehicle is running on via a Mr. Fusion device. This is from the Back to the Future movies. Is fusion a solution? There are articles in the press just this week where MIT thinks they found a solution of bringing us fusion power in under 10 years. Hey, that's better than the 50 years we've always heard that fusion power would be here. Quickly, IEEE, here's a information source that's updated every day. It's on the Flipboard Foundation. This address will be in your download, and you can read about the latest technology of batteries every single day. Here's the LinkedIn group, and here we'll post an entry for this webinar. So get your questions ready. We're going to answer them in the days ahead. This slide has a little bit of date. At the moment I captured this slide, there were 55,000 articles in the IEEE Explorer library of scientific papers. There are now 59,000 articles that I checked and found just last night. So stick with the IEEE. We know best how to utilize these technologies that the electrochemists are producing. So here's a chart of how to find out more. And I've been fair and balanced, as they say. Not only does information come from the IEEE, but from other parts of the world, including a lot of work going on in Japan, Europe, and China. The future of battery technology is a worldwide problem and a solution. And then lastly, giving back some time to Mark, let's do the right thing with our electric energy. There are still parts of the world that don't have reliable or any electricity at all. So if you're an engineer, how about come up with an application or device to help us make the use of electricity 100% across the whole world? So with that, Mark, you are in charge. Let's take a couple of quick questions.
Okay, Lee, thanks for all that material. That was really in-depth, and I learned quite a few things there. I'm going to look, see, I don't think I saw any questions come in. I'm not seeing any. And it looks like there were a few links shared on the chat line, but those will be sent out also. I put the wrong group here, Lee. I apologize. I thought it was the Internet of Things group, but, which I didn't see in your list. But for those that are going to be sending questions, make sure you look at Lee's, the end of his presentation, where he references the IoT battery group on LinkedIn. That's where the questions will be taken from. But Lee's also the manager of the site, IEEE Internet of Things group on LinkedIn, which you can contact him at also. So if you have more questions, as we mentioned, the LinkedIn groups, but also you can contact Lee at this email address. There's also the IEEE Internet of Things Initiative website. And if you have any compliance questions or projects coming up, you can contact us at Washington Labs. We'll be glad to take care of that. I do want to notify you about some upcoming IEEE events. Next month, I'll be at the IEEE Product Compliance Engineering Symposium in San Jose. Been building up a really good conference out there. It covers all aspects of compliance: EMC, product safety, medical, industrial, environmental, recyclability, just about any concept of compliance you can think of having to do with products. The Global IoT Summit is going to be coming up in June in Bilbao, Spain. There's actually an event this week in Tuscany, Italy, but that's on this Friday, and I didn't figure any of y'all were going to rush to make it over there if you hadn't already registered for that. And then end of July and beginning of August, there's the IEEE EMC Symposium. It's the last several years been in conjunction with the Signal Integrity and Power Integrity Group. So if you're interested in power concepts, EMC concepts, those are real good to attend. Also, it's not listed here, but there is an international EMC Symposium in Singapore this year if you were interested in that. I mean, you always contact me for more information. I've provided my IEEE email address down there. So I want to thank y'all for attending today. I'll let you know about the next coming up webinars. Next month we'll be covering Middle East compliance, part of our monthly series of international approvals. And in June on Central America and the Caribbean, and in July we'll be covering South America. So we'd like to have y'all join those there. They're always free. You can register at the Washington Labs website at the Academy web pages, which you can see there. I want to thank all of y'all for attending, especially thank Lee Stogner for joining us today to provide his insight into IoT and the power, the battery technologies, and just the wealth of information provided there. Be sure to check out those links he included in there to all the different IEEE groups, which cover various aspects of these issues and products. And on behalf of Washington Labs Academy, I want to thank you all for being here today, and we'll see you next time.
Goodbye.